This tutorial shows you how you can find the optimum winding for a maxon motor. Starting point is a given motor type that has been selected previously according to speed, torque and service life considerations. Please refer to the corresponding maxon selection videos for more details. For a given motor type, you can choose between different windings. The purpose of the winding selection is to match the available electrical power, current and voltage to the required mechanical output power of the motor. It is torque and speed. The different windings of a motor type are listed in columns, the resistance increasing from left to right. The first winding on the left is made with a wire of the largest diameter. Accordingly, its resistance is low and the currents needed are high, however, at a low voltage. The last winding on the right is made with the thinnest wire. The resistance and the needed voltages are high, but there is only a low current flow. Looking at the mechanical output of the different windings, we observe the following. The mechanical motor limits are almost identical over the winding series. The maximum speed remains the same. The nominal torque, it is the border of the continuous operating range, is almost identical for all the windings. The speed-torque line describing the mechanical behavior is almost identical too. It's about 175 rpm per millinewton meter in this example. The particular nominal voltage of each winding is selected to give a similar no-load speed for all the windings. Essentially, this means that from a mechanical point of view, there's hardly any difference between the windings. Each one can do the job. The difference lies in the electrical characteristics. Here is a graphical representation of the findings of the previous slide. The operating range diagram of one winding can stand for the full winding series. The speed-torque lines lie in a narrow band and start at similar no-load speed. This is how the nominal voltage is assigned to each winding. For a particular application, however, the available voltage is given and the objective is to reach all the operation points with this voltage. Usually, the most demanding operation occurs at the end of the acceleration. It is the one at maximum speed and maximum torque. All the other operation points can easily be reached by reducing the voltage, a task usually done by the controller. Therefore, let's concentrate on the extreme operation point and see how the different windings can reach it with the available voltage. Selecting the winding with 24 volt nominal voltage, similar to the available voltage, may not be the right choice. Here the acceleration cannot be fully achieved. The winding to the left in the catalogue with a higher speed constant of 705 rpm per volt and the nominal voltage of 18 volt covers all operation points easily when operated at 24 volt. A speed or position controller will adjust the motor voltage to the lower values needed. However, the current to reach a particular torque is higher. The windings with 12 or 9 volt nominal voltage won't make good use of the 24 volts available, and the currents needed are even higher. The remaining two windings with higher nominal voltage cannot reach the required speed because the speed constant is too low. In other words, the winding selection is a matter of calculating the minimum speed constant required to reach the speed under load. Given the peak torque and maximum speed of the application as well as the available motor voltage, we calculate the speed constant that theoretically can just fulfill the task. The formula uses the speed and torque of the extreme operation point and delta n over delta m, the typical or average speed-torque gradient of this motor type. From a graphical point of view, the formula calculates the no-load speed associated with this operation point and divides it with the available voltage at the motor. Selecting the optimum winding is now a question of comparing the speed constant of the different windings with this minimum value. What we need is a speed constant larger than the calculated one. Let's illustrate this with an example. Assuming that the extreme operation occurs at 10,000 rpm and 19 millinewton meter, With 175 rpm per millinewton meter speed torque gradient and 24 volt supply voltage, we end up with a speed constant of at least 555 rpm per volt. A glance at the catalog page shows in line 13 that the first 3 windings fulfill this condition. The winding with 24 volt nominal voltage is just a little short. Selecting the winding with 18 volt nominal voltage gives us a nice speed reserve. The speed torque line lies above all operation points. Optimally, the selected speed constant should be about 20% higher than the calculated one. This gives us some headroom for proper control and to account for all kinds of tolerances. However, do not select a speed constant that is too large, because this means that the available voltage is not used well and that you need a lot of current from power supply and controller. A remark just to make things clear. Do not refer to the nominal voltage for the winding selection. The nominal voltage is just the reference voltage for specifying motors. It's irrelevant for the motor selection. That's it. A short introduction on winding selection. In conclusion, the optimum winding uses the available voltage well and requires the lowest possible current. And don't forget, you have to know the extreme load operation to make a proper winding selection. Good luck!